Okay, so hello class, welcome back. So in this recording, we're gonna take a look at the first section on chapter 5, which is the idea for chapter 5, which is about the probability. So in the first section, 5.1, we're gonna talk about probability rule. What is the rule for the calculation of the probability? So let's give you the first definition before we give you more definition, right? So a phenomenon is random. A phenomenon is random if the individual outcomes are uncertain, but there is nonetheless a regular pattern of outcome in a large numbers of repetition. So that's going to be the definition of random, right? So a phenomenon is random if the individual outcomes are uncertain, but there is nonetheless a regular pattern outcome in a large numbers of repetition. So for example, when you flip a coin, right? So if we're gonna flip a coin and then I'm not showing you the results of that, right? What's it landed, but I'm gonna asking you, oh, what's gonna be the outcomes of this one? So the only thing that you can know is you can say that the outcome will be either a head or a tail, but do you know exactly what's the outcome it's gonna show? You have no idea, right? So you only know that when you flip a coin, there are two possible outcomes that's gonna be head or tail. So in the general pattern, in the long run, when you have the repeat of that process a longer time, there is some general pattern of that outcome. But do you know exactly what's the next outcome gonna be? There's a no, right? So that's gonna be random, yeah. So a phenomenon is random if individual outcomes are uncertain, but there is nonetheless a regular pattern of outcome in a large numbers of repetition. Now, what is a probability? So probabilities measure the likelihood of an event occurring. So what is the probability? So probability is going to show you the likelihood of an event occurring. Look like what's the probabilities is going to rain today. Okay. The next definition is an experiment. So what is an experiment? An experiment is a repeatable process where the results are uncertain. So an experiment would be look like you flip a coin, you draw a card from a standard deck of cards, you roll a die. So that's going to be an experiment. So it's going to be a repeatable process because you can actually repeat that process again and again and again, right? But the results is not sure. We don't know exactly what's going to be the outcome. So the set or the list of all of the possible outcome in an experiment is the sample space. So the sample space is the collection for all of the possible outcome from an experiment. So for example, when you flip a coin, then the possible outcome gonna be head and tail. So that's gonna be the sample space. When you roll a die, there are 6 possible outcomes, right? 1, 2, 3, 4, 5, 6. So when you list out all of the possible outcome, that's gonna be the sample space for the experiment of rolling a die. 1, 2, 3, 4, 5, 6. An event E. We're gonna use the uppercase letter to show the event is, and once again, we're gonna use the letter S, uppercase S to show the sample space. So the sample space uppercase S, and then we're gonna use an upper letter to show the event. An event is a collection of the possible outcome. An event is a collection of possible outcome. An event with one outcome, I sometimes call it the symbols event. So that's going to be symbol event when we have one outcome. So those are a few definitions that we have related with the probability. So now we're going to take a look at example number 1 to give you better ideas of those definitions. The experiments involving a fair six-sided die. So we assume that this is a fair six-sided die. This is a common die that we have, right? So we have a six-sided die. We note the side that's going to land up, right? Now question A, determine the sample space. So the experiments involving a fair six-sided die. So the sample space is the list of all of the possible outcomes from this experiment. So we're gonna use in the uppercase S to show the sample space. So we're gonna list all of the possible outcome when you roll a die. So what are the possible outcome that we might have when you roll a die? So when you roll a six-sided face, right? So when you roll a fair six-sided die, then there will be 6 possible outcomes. So the outcome could be a 1, could be a 2, could be a 3, could be a 4, could be a 5, could be a 6. So this is going to be the sample space. When you list all of the possible outcome from an experiment, that's going to be the sample space. And once again, we're gonna use the uppercase S letter to show the sample space. Now event E. So event E, what's in the event E then? So the event E is a rolling uneven number. Okay, so this is gonna be event E, right? So event E is a rolling uneven number. So what's gonna be the possible outcome for this event? So when you run a six-sided die, right? So you're gonna get from 1 to 6. Which one of them gonna be even? So the even number will be 2, 4, 6, right? So there are 3 possible outcomes for this event. So this event has 3 possible outcomes. So this event is not a simple event, excuse me. Yeah. So this event is not a simple event because they have 3 possible outcomes. Okay, so sample space is one of the possible outcome from an experiment. The event is the collection for the possible outcome under the condition of that event E. Yeah, so event E is a rounded even number. Even number from the sample space, we got 2, 4, and 6. Okay. So that's going to be example number 1. I hope that's going to give you a better ideas of the definition for event and experiment and the sample space, right? Now let's try another question, then example number 2. Consider the probability experiment of having 2 children. Okay, so having 2 children. So a couple decided to have 2 children. We know the genders of the 2 children. So the genders of the 2 children could be a boy or a girl, right? So determine the sample space. Okay, so determine the sample space. So the sample space is going to be the genders of the 2 children. So what are the possible genders of the 2 children, everyone? So the first case, you might have 2 boys, right? So the couple will have 2 boys. They might have, the first one is a boy, the second one is a girl, or vice versa. The first one is a girl, the second one is a boy, or they might have 2 girls, right? Okay, so this is gonna be the possible genders of the 2 children. Yeah, so could be 2 boys, the boy first and the girl first and the boys, and then 2 girls. So that's gonna be the possible outcome from this experiment of having 2 children. So this is gonna be the sample space. Now from this sample space, we determine the event E. So event E will be, what is it? Event B is have 1 boy. Okay. So what's the possible outcome? That's gonna give you 1 boy. Okay. So take a look at the sample space so we can extract the possible answer, the possible outcome that's give you 1 boy. So it could be a boy and a girl, right? Or it could be a girl and a boy, right? So this is gonna be having 1 boy. Okay. So that's gonna be this event E. So event E's have 2 possible outcome, boy, girls, girl, boys. Yeah. Okay, so this is the second example, everyone. Now let's give it a try for the third example, right? An experiment consists of rolling a dice and tossing a coin. Find the sample space of this experiment. Okay, so what's going to be the sample space of this experiment when you roll a die and you toss a coin? So when you roll the die, there are 6 possible. We will consider this is a 6-sided dice, and then the coin is going to be head or tail. Now we're going to list out all of the possible outcome for this experiment, right? So let's see what's going to be the possible outcome. Now we need to find out the sample space. We need to show all of the possible outcome there. So we're going to roll the die first, right? So a die could be 1 and head, 1 tail, 2 head, 2 tail, 3 head, 3 tail, 4 head, 4 tail, 5 head, 5 tails, 6 head, and then 6 tail. Okay. So those are the possible outcome for this experiment of rolling a 6-sided dice and then you toss a coin. Okay. So we have 12 possible outcome. So that's going to be the sample space. So the sample space is a collection for all of the possible outcome from an experiment. So when we're working with the probabilities, everyone, it's very important for us to know the sample space because that's going to be one of the value for your calculation of the probability. Okay, so that's gonna be the definition related with the probability, right? So probability, experiment, sample space, and then event. Okay. Now we're gonna take a look up the rule for the calculation of the probability. So what are the rule for the calculation of probability? So the rule of probability. So the probabilities of any event, yeah. So rule number one, the probabilities of any event, we're gonna use in this notation PE. So PE is the probabilities of event E. So the probabilities of any event E must be greater than or equal to 0 and less than or equal to 1. So the calculation for the probabilities gonna stay between 0 and 1 inclusive. So PE is more than or equal to 0, less than or equal 1. And then the second rule of the probabilities is the sum of the probability for all of the outcome must be equal 1. The sum for all of the probability for all of the outcome must equal 1. So when you take PE1, PE2 plus on the way up to PEN, the total should be equal 1. So based on rule number one, we say that the probabilities of an event could be 0, could be 1, right? It's going to be any value between 0 and 1, but there are some cases the answer for the probability could be 0, could be 1. So if an event is impossible, then the probabilities must be equal to 0. Yeah, so impossible event, which means that the probability will be equal 0. If an event is certainty, so certainty, which means that the event for sure will happen, then the probability is equal 1. Okay. So equal 1, it means that it's always happen. Zeros, it never happen. An unusual event is one that has a low probability. So how low the probability is going to be? So when we say low probability, which means that the probability is 5% or less. So that's going to be unusual event. So unusual event, which means that the one have low probabilities of 5% or less. So that's how we determine unusual event if the probabilities is less than or equal 5%. So that's the rule for the calculation of probability. Now, probability models, how can we determine if we have a probability model then? So a probability model lists the possible outcome of a probability experiment and each outcome probability. So they're gonna list the possible outcome of the probability experiment and then they're gonna show the corresponding probability. A probability model must satisfy rule number 1 and rule number 2 of the rule for probability. So we might use in the rule number 1 and rule number 2 to determine if we have a probability models. Okay. Now let's apply that. The definition of the probability model determines if we have a probability models. At the table below a probability model, can you explain why or why not? Okay. So we're gonna use in rule number 1 and rule number 2 to determine if this is a probability models. Then okay, I will take this down. Okay. Now the first requirement that we have to double check is I'm gonna use in the bullet then. Okay. So for the first probability, we want to make sure that 0 is less than or equal the probabilities of event E, and this is gonna be less than or equal 1. And then the second property that we need to double check is the summation for all of the probability should be equal 1. Okay. Okay, so the summation for all of P E I. Okay. Okay, so we're gonna use those two conditions to double check if it's good or not, right? Now the first characteristic, you want to make sure that the individual probability ranges is between 0 and 1. So look like all of those numbers is between 0 and 1. So this is gonna be good, right? So we can say, oh, this is gonna be a check one, right? Yeah, so the first one is check. How about the second one? Okay. So the first one is check. Okay. Now, how about the second one? Is it true or false? Now, the next thing we do is when we do the total for all of this probability, the answer should be 1. 0.03 plus 0.7 plus 0.15 plus 0.13. Are they equal 1? So the answer is 101. Okay, so the answer is 1.01, which is more than 1. So it's failed, right? Okay. So it's good with the first condition, but it's failed with the second condition. So I'm going to say this is not a probability model because it's not true with the second condition. So in order to be the probability model, it must satisfy rule number 1 and rule number 2 of the rule for probability. So rule number 1 is good, but rule number 2 is not good. So that's why this is not a probability model. Now, how about the second one? Is it a probability model? Yes or no? So I'm gonna use in the 2 condition again, right? So I'm gonna use in the 2 condition. So let's use in that condition to check then. So rule number 1, is it good? So 0.50 is between 0s and 1. 0.07 between 0s and 1. Yeah. Now 0.12 is between 0s and 1. 0.31 between 0s and 1. So that's good. So this is check. Now how about the second condition? Are they sum up equal 1? Yes or no? Let's double check then. 0.5 plus 0.07 plus 0.12 plus 0.31. Okay. It's equal exactly 1, so check. Okay. So the second condition is also true. So it's satisfied for the 2 condition, right? It satisfied with the 2 rule for rule of probability. So I'm gonna say this is a probability models. Yeah, yes, this is a probability model. The first one is not, the second one is good. Okay, so that's how we determine the probability models. Now we're gonna moving on to the big ideas of this section is the calculation for the probability. So what's the different method that we might use it to calculate the probability? So the first option, we can use an empirical rule. Yeah, so empirical method to calculate the probabilities, empirical methods. Approximating the probability using empirical approach or empirical methods. Okay. So what's the ideas of the empirical approach or empirical method to calculate the probabilities? If we do not know the probabilities of a certain event, and we might conduct a series of experiments to approximate it. Yeah. So we might conduct a series of experiments to approximate the probability. Then the probabilities of event E will be approximately equal the relative frequencies of event E. So you can remember how we calculate the relative frequency from chapter 2, right? So the relative frequencies of event E is equal the frequencies of that event E divided by the numbers of trial of the experiment. So how many times that we repeat that experiment, and among that many of times that we repeat the experiment, how many times that the event E will occur. So that's the calculation of the relative frequency that can help us to approximate the probabilities of event E. So let's give it a try right here, everyone. Okay, so a French naturalist, this person tossed a coin 4,040 times. So he tossed a coin 4,040 times. So this is the numbers of trial of experiment. And he find out that 2,048 of them gonna be head. Okay. So among 4,040 times that he tossed a coin, he got 2,048 head. Approximate the probabilities of getting a head when tossing a coin. So for this question, we're gonna use the empirical approach because we can actually conduct the experiment. So the probabilities of getting head will be equal the frequencies of event E divided by the numbers of trial, right? So this is gonna be the formula right here. I will just copy that then, okay. So it's equal the frequencies of event E. So event E was getting ahead. So the frequencies of event E is 2048. Out of the numbers of trial of the experiments is 4040. Yeah. So among 4040 times that he tossed a coin, he got 2048 head. So we're gonna perform this calculation, 2048 divided by 4040. So this is gonna be the approximation of the probabilities of tossing a head, right? So flip a head, yeah. Okay, so gonna be 0.507, and we round the answer to 3 decimal place, 0.05, yeah, 0.507, yeah, so 0.507, okay. So this is gonna be the approximation of the probability that we will get in head, okay. So this is the first approach. We're gonna use the empirical method to approximate the probabilities if we can actually conduct the experiment, and then we can keep track of the numbers of time that the event E occur. So example number 6 is another question that apply the empirical approach or empirical methods based on the relative frequency. Okay. So let's give it a try. You can take a look at this question right here. So in order to approximate the probabilities of those events or those outcomes, we can do this relative frequency, right? The probability of those outcomes, we can base on the relative frequency because we did actually approaching this, right? We actually perform those experiments and then we have those outcomes, yeah. This is the frequency for those outcomes, yeah. So a class of 52 students run the peak 3,939 times, and then among that many times we have no frequency, right? Okay. Now we're gonna use the relative frequency to answer this question then. Use the results of the experiment to build a probability model for the way the peak land round to 3 decimal place, okay. So we're gonna do each division right here, right? So the first division for the probabilities of side with no dot, it's gonna be 1343 divided by 3939. Yeah, 3939. Let's see what's the answer then. So it's gonna be 1343 divided by 3939. We have 0.341. Okay, 0.341. Similar idea for the next one. We're gonna do the side with dot, 1294 divided by 3939. 1294. So gonna be 0.329. So 0.329, 0.329. Now Razorback is Razorback gonna be 767 divided by 3939. 767 divided by 3939. Okay. 0.195. Okay, so 0.195. The next ones we're gonna do 365 divided by 3939. 365, yeah. 365 divided by 3939. 0.09326, right? So we're gonna round it to 3. 0.093. Okay, 0.093. Now the next one is 137 divided by 3939. 137 divided by 3939. 0.035. 0.035. And the last one, we're gonna do 32 divided by 3939. We will see what's the answer then. 32 divided by 3939. 0.008. Okay, 0.008. So that's going to be the probability based on the relative frequency. We take the frequency divided by the numbers of trial. That's going to be the relative frequencies, and we're using this relative frequency to approximate the probabilities of those events or those outcomes. Now, question B, the probability that you're gonna throw the pick and it's gonna land it on the side with dot. So what's the probability that you will have the side with dot? So the side width dot will be based on the table. We got 0.329. Okay, 0.329. So that's the probability that you throw the pick and then it will land it on the side width dot. So what's the meaning of this calculation? Okay, so what does it mean by the values of 0.329 in this application? So which means that in 1,000 times that you're gonna throw the pick over here, we would expect about 329. How we gonna get that number? Because we're gonna do 1,000 times, we take 1,000 times this number. So you're gonna get about 329 times. It's gonna land it on the side with dot. Okay. So this is the first option, the first method that you might use it to calculate the probabilities of an event. If you can actually conduct the experiment, we're gonna use the relative frequency to approximate the probabilities of an event E. So do we have any other choices that we might calculate the probability then? Okay. So before we're going to talk about the next method to calculate the probability, let's give you the ideas of the laws of large number. So A, the numbers of repetition of a probability experiment increase the proportion with which a certain outcome is observed get closer to the probabilities of that outcome. So when you can repeat the number, when you can repeat this experiment again and again and again, and that number get increased larger and larger, the proportion with which a certain outcome is observed get closer to the probabilities of that outcome. So we can use the proportion as an approximation of the probabilities of that outcome. So was imprisoned by German during World War II, a South African math person tossed a coin 10,000 times, and he got 5,067 heads. So the proportion of heads is, we're going to take 5,067 divided by 10,000. That's how we got 0.5067. Now, around 1900, an English stat person tossed the coin 24,000 times and result 12,012 heads. So we're going to take the 12,012 heads divided by the numbers of experiment, the repetition of the experiment, 24,000. So we have the probabilities of heads a 0.5005. So based on this, those experiments, we can say that probabilities of getting a head get closer to 0.5 and the numbers of toss increase. Okay, so the probabilities of getting a head gonna get closer and closer to 0.5 when the numbers of toss get increased larger and larger. So based on this idea, the loss of large number, we might have the second option. That's we can calculate the probability, which is the classical methods. Okay. So what's the classical method then? The classical methods apply to experiment where all possible outcomes have an equally likely outcome. So we can apply the classical methods when all of the outcomes are equally likely outcomes. So they have the same chance of being occurs. So the same probabilities of occurring for all of the possible outcomes. So like when you roll the die, when you flip a coin, yeah. So when you roll the die or when you flip a coin, each of the outcomes are equally likely, yeah. So what's the ideas of the classical method? Okay. So if an experiment has n equally likely outcome, so if they have n equally likely outcome, and if the numbers of ways event E can occur Cm, the numbers of ways that event E can occur Cm, then the probabilities of event E, Pe equal the numbers of possible ways that event E can occur over the number of possible outcomes. So that's how we calculate the probabilities of event E using the classical methods or classical approach. It's equal the numbers of ways that event E can occur over the number of possible outcomes. So in this case, we using the letter S to show the sample space, and then E is the numbers of where event E can occur. Yeah, so the numbers of where event E can occur, NE divided by the numbers of sample space, the number of possible outcome from the sample space was the NS. So this is the classical methods. We are assuming that all of the possible outcome will be equally likely. Yeah. So now we're going to take a look at an application of the classical approach or classical methods. Okay. So example number 7. A coin is tossed 3 times. We're going to take note the side that's going to land it up, right? The coins are going to toss it 3 times, right? So let's see what's the possible outcome first. So a coin is tossed 3 times, find the sample space. Okay. So let me help you with the sample space first, everyone. Okay. Now you might have this look like you do the coin 3 times, right? You might have 3 heads in a row, look like this. Or you might have 2 head and 1 tails, and I will scramble this. So head, head, tail, head, tail, head, or tail, head, head. Okay. Now you might have look like head, tail, tail, look like this. And then I will scramble it. So gonna be tail, head, tail, or that's gonna be tail, tail, head. And then the last possibility, you're gonna get none of them gonna be head, right? So gonna be tail, tail, tails. Okay. So when you flip a coin 3 times, when you flip a coin 3 times, there are 8 possible outcomes. So there are 8 possible outcomes. So this is gonna be the sample space. Okay. So now we know the sample space already, the number of possible outcomes, right? So the number of possible outcomes is 8. Okay. The number of possible outcomes is 8. Now, based on this, we can answer the next question. Compute the probabilities of flipping head first. So what is the probability that you will flip head first? Okay, so the probability of you flipping head first. So the first outcome will be head. The first one will be head. The first coin gonna show you a head. So let's see what are the numbers of way that will show a head first. Okay, so it's equal the number of way to flip head first over the number of possible outcomes. Okay, so let's take a look at the sample space, everyone. How many possible ways that you can get the head first? So the head first is this one. The first one is a head. That's what I mean. So this is gonna be the first one is head. This also the first one is head right here. Head, head, tail. The first one is a head. This one is the first one is a head also. And then this one, the first one is a head. Okay. So based on the one that I changed the color, right? So those are the outcomes that give you the head first. So we have 4 possible outcomes that's gonna give you head first. Now, what's the number of possible outcomes? So the number of possible outcomes, we're gonna get 8, right? Okay. That's gonna be 4 over 8. Can you reduce this fraction? Yes, right. There is a common factor of 4. We divide both of them by 4, so we have the answer say 1/2, or you can get the answer as 0.5. Okay. So this is the probability that you will flip head first. Okay. So we're just using the classical method to calculate the probabilities, assuming that all of the outcomes are equally likely. Now we can try the next question together, everyone. So a pair of fair dice is rolled on possible outcome are listed below. So now you're gonna run a pair of fair dice. So there are 2 die, right? You're gonna run 2 die, then those are the possible outcome we have from the 2 dice. Okay. Now let's see. Based on this possible outcome, we got 36 possible outcome, right? When you roll a pair of fair die, there are 36 possible outcome. Now compute the probability that the sum is 7. So what among the 36 possible outcome right here, how many of them gonna give you the sum is 7? The sum of the 2 face is gonna be 7. The sum is 7. So let's list the possible outcome of 7 first. Okay, so let's list the possible outcome that's gonna give you a 7. So it's gonna be, let's see the sum of 7, then the sum of 7. So we can have this group right here, right? So it could be 6 and 1. Or you can have what else? So 6 and 1, right? or that's going to be 5 and 2, or that could be, so this is going to be 6 and 1 right here, 5 and 2. Now I'm going to go 4 and 3. And what else? So 4 and 3, now we're going to go 3 and 4. And now we're going to go, what is it? 3 and 4, 2 and 5. And then the last one going to be 1 and 6, yeah. So those are the possible way that we can get the sum of 7, right? 6 and 1, 2 and 5, 4 and 3, 2 and 3, 2 and 3 and 4, 4 and 3, 3 and 4, 2 and 5, 1 and 6. So those are the sum of 7. Yeah, so no horizontal line right here. Gonna give you the sum of 7. So we have 1, 2, 3, 4, 5, 6. Yeah, so the probabilities of event is equal the numbers of ways to run a sum of 7 over the number of possible outcomes. Okay. So the numbers of ways that you can run the sum of 7, we have 1, 2, 3, 4, 5, 6, right? So there are 6 possible ways that you can run a sum of 7 out of the number of possibility, which is 36, right? So that's going to be 36, yeah. Okay. So now 6 over 36, we can reduce in this, right? So the answer is 1 over 6. You might divide it to get the approximate answer. So 6 divided by 36 then, okay. That's going to be 0.166666, right? So that's going to be repeat the 6, yeah. So going to be 0.167. I will round it to 3 decimal place, yeah. Okay, so that's how we calculate the probability that the sum will be 7. Now, you can give it a try for the next question, right? Let's see what's going to be the answer for question B. Compute the probability that the sums is less than 5. The sums is less than 5. Okay, so this sums is less than 5. So let's list the possible outcome that's going to give you the sum less than 5. Okay, so how many possible ways that we can get the sums is less than 5? So let's take a look. Oh, so the sum could be 1 and 1. So 1 and 1 is 2 less than 5, right? Or what else? We can get 2 and 1. That's going to be 3 less than 1, or 1 and 2. It's still less than 5. We can get 3 and 1, which is 4. 3 and 1, 2 and 2 is still less than 5, or 1 and 3. Okay, can we do more? Can we do 4 and 1? Yeah. 4 and 1 is 5, but we want to get less than 5, right? So this is less than 5, so we're not going to accept that case, yeah. So 4 and 1 is 5. That's it, not less than 5. So that's all. Okay. So how many possible outcomes we got? So we got 1, 2, 3, 4, 5, 6 again. Okay. So we have 6 possible outcomes. Yeah. Okay. Now we are ready to calculate the probabilities of this. Yeah. So what's the probabilities of the sums is less than 5? So I'm gonna use the classical method. So it's equal the numbers of ways. The numbers of ways to run a sum less than 5 over the number of possible outcomes. Yeah. Okay, so let's take a look at this question right here, right? So that's the way that we just listed right here, right? So how many possible ways that we can get the sum less than 5? 1, 2, 3, 4, 5, 6, right? So there are 6 possible ways that you can run the sum less than 5 over how many possible outcomes that we have. So we have 36 possible outcomes. So it's going to be 36. So 6 over 36. So 6 over 36, then we might reduce in this fraction. So we have the answer, say 1 over 6. And when you divide 1 over 6, you have the answer 0.167, look like what we have earlier. Okay. So this is the second example that gave you the idea how we're using the classical method to approximate or to calculate the probability. So whenever we're using the classical method, make sure that you have to assume that we have all of the outcomes are equally likely. Yeah, so n is equally likely outcomes. Yeah, so that's gonna be the classical methods. Okay. Okay, so we okay with the classical method. Now we're gonna move it on, take a look at the next one, which is the subjective probability. So you might have this in reality, subjective probability. So what is a subjective probability? So a subjective probability is a person estimates of the chance of an event occurs. So this looks like personal estimation. Yeah, so this is gonna be a personal estimation. This probabilities is based on personal judgment. It's based on the personal judgment. So it's based on your knowledge, based on your study. Yeah, so it's going to be based on the personal judgment or based on your feeling also. Subjective probability should still between zeros and one, but may not obey the laws of probabilities. Yeah, so it's still the answer for this probability is still between zeros and one inclusive, but maybe they might not obey the laws of probability. So for example, if you're gonna take a look up the skies and you can estimate, oh, what's the probability that it's gonna rain today, right? So everyone will have a different estimation of that, right? All of us we're not gonna get the same answer because it's based on your personal judgment or your personal estimation. Yeah. So for example, an economist predicting that there is a 20% chance of recession next year. So this is based on his study, based on his calculation, based on his research. Then he said that about 20% chance of recession for next year. So, but based on when you asking a not the person, not the economist, then they might have different prediction for this probability. Yeah. So this is the subjective probabilities. Yeah. So there are three different options that you might use it for the calculation of probability, right? You might use in the empirical methods, you can use in the classical methods, or you can use in the subjective probabilities, okay? So this is the first section 5.1, which is the introduction with the probabilities. I will stop the sharing at this point, everyone, and I will stop the recording at this point. You can go back and try the homework for section 5.1. I will see you next time for the next recording. Yeah.